Hi, everybody. Today we're talking about independent samples t-tests. So let's dive in. What we've got over here on the right is ultimately the equation that we need to end up with, right? And we're going to try to find what are all the little pieces involved so that we can figure out what this equation tells us about the t, the value of t, or the observed t-score for our data. So what this is saying is that we're going to take the mean of the first group or the first sample, x bar sub 1. We're going to subtract from it the mean of the second group or second sample, mean x bar sub 2. And then we would subtract this part over here is the representation of the null hypothesis in an independent samples t-test. So what this is saying is that mu1, that is the population mean, minus mu2, should equal 0 because the null hypothesis is that the means are the same, that there is no difference between the means of the two groups. So if you subtract one number from itself, you get 0. So we basically don't even worry about this part of the equation, which is kind of nice. Now on the bottom, this is not to be confused with standard deviation. This is the standard error, or really the estimated standard error. And the full name for this one is called the estimated standard error of mean differences, but we'll just call it the estimated standard error. Every time we've calculated a t, whether it's a one sample t-test, a paired samples t-test, or now an independent samples t-test, we're basically always looking at mean differences on the numerator and then an estimate of standard error on the denominator, right? And that's what we've got here as well. But this one's going to be a little bit more complicated, okay? So how do we figure out what the estimated standard error is? Well, it's going to be this second equation over here, which is a little bit complicated looking. It's the square root of pooled variance, the pooled variance for both of the groups divided by sample size of the first group plus the pooled variance for both of the groups divided by the sample size of the second group. Well, we don't know what pooled variance is yet. We haven't figured that one out. Well, that's why we need the third equation. Yes, three different equations that we're going to have to solve for. This s squared subscript p, that is the pooled variance, because remember, variance is the standard deviation squared. So this is the pooled variance, and it equals the sums of squares for the first group plus the sums of squares for the second group divided by degrees of freedom of the first group plus the degrees of freedom for the second group. Now, this is important. Each group has a degrees of freedom of n minus 1 in this test. If you add them together, though, that means that you're basically saying, I want everybody in the entire study, so all the entire sample size of both the groups combined, minus 2. So n minus 2 is what one way you could think about this, or degrees of freedom of group 1 plus degrees of freedom plus of group 2. That's the same thing as n minus 2 overall. All right. So basically, what we need to do is we'll probably start kind of with pooled variance and work our way up because that slots into this equation, and then once we find estimated standard error, that slots into this equation in the denominator, and then finally we can find our observed t-score. So that is where we're headed. Let's look at the data that we've got here. We've got 13 participants, it looks like, and they have a preference. They're either cat people or they're dog people, right? They like cats or they like dogs. And then we've got their extroversion scores on a scale of 1 to 10. So we could make the directional one-tail hypothesis that on average, dog people will be more extroverted than cat people, right? I think that might make sense. So we can test that hypothesis using an independent samples t-test. Now, unfortunately, the way that our data is currently arranged, you've got to rearrange it into something kind of new where you actually split out all the cat people and all the dog people, right? And so what I've already gone ahead and done is something like that, where I've taken all the cat folks, all the dog folks, and then each of these scores represents their extroversion, their score for one single participant on their extroversion rating. So I'm gonna take all this stuff and I'm gonna bring it up here to help us out. Okay, and you'll have to do this on your own if I just give you raw data. So a good idea to take a look at this. You make, a separate column for each of the groups. This cat person, the first cat person's got an extroversion score of 3. The second cat person looks like they're down here and they've got an extroversion score of 4. So you just keep going down the list and pull them out like that. All right, so now how do we begin? A little bit of dealer's choice. One thing we might want to do is start with the means, and then we'll probably have to jump down to pooled variance. So let's start with the means. By the way, you can see that there's different sample sizes, right? Like there's different amounts of people in each of these groups. And when this is the case, and it most often is the case in real research, you rarely ever get exactly the same number of people in both groups. You have to use the pooled variance equation, okay, to calculate estimated standard error. If there were the same number of people in both groups, you could actually use a slightly different equation that's a little bit easier. But if you use this equation, you always get the right answer, no matter how many people are in the sample, whether it's even numbers or different numbers in different groups. So we always prefer to use this because it's like you're going to get the right answer. You don't have to memorize two different equations or look up two different equations. So let's go ahead. I'm going to start with the mean. So we're going to just give ourselves some little headings here. Again, to find the average of a group of numbers, you just type in equals and start typing in the word average. Double click on that. Drag and drop the numbers that you want. And that's the mean for the mean extroversion rating for cat people in this sample. Let's do the same thing over here. Equals average. And the average extroversion rating for dog folks is 5.86. Now, this is an important distinction. You might just look at these numbers and say, hey, these are different numbers. It looks like the average extroversion rating of dog people is higher than the average extroversion rating of cat people in this sample. I'm done, right? Well, that's the hypothesis. We solved it. No, 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 no. These numbers are, in a sense, absolutely different from each other, right? Like, obviously, 5.86 is a higher number than 4, but we do not know if that difference is statistically significant. Because if it is not statistically significant, if we run the test and we find out that the t-value that we observe does not lie in the critical region and we fail to reject the null, what that means is that 5.86 is not statistically significantly different from a mean of 4. And therefore, you cannot say that these two numbers are different from each other. So that's something that you really want to pay attention to because it's like, yeah, obviously they're different numbers, but the question is not whether they're different, it's whether they're significantly different. Okay, so let's dive in. And I think what we're going to do, remember, now we've got the means. So we've got kind of the numerator taken care of, but we need to find the estimated standard error now. And to find that, we need the pooled variance. And so let's start with the pooled variance, right? What this is saying is that the sums of squares for group 1 plus the sums of squares for group 2 divided by degrees of freedom of group 1 plus degrees of freedom of group 2, that's the pooled variance, okay? So what we need to do actually is similarly to all the way back when we were trying to hand calculate standard deviations. First of all, we need to get a deviation score for each of the participants from the mean. So we're going to start with the deviation score. Deviation score is simply type in equals the first score minus the mean. And remember, you're going to have to put in these dollar signs, and that's to kind of keep it each of these rows subtracting the mean instead of it would kind of misplace what it's trying to do. So again, we got the first participant's score minus the mean. 3 minus 4 should give us -1, so that looks good. Now you can drag this all the way down and it'll automatically populate the deviation scores. These are all the deviation scores for each cat person in terms of their extroversion, right? So now we don't have to go through and normally we would, to find the standard deviation and then, or the sums of squares, I guess, we would take the deviations and we would square them and then we would add them together. That would give us literally the sum of the squared deviations or the sum of squares. Excel has a function for sum of squares, but you do need to get the deviation scores. You can't use the sum of squares function on the original raw data. You do need to get the deviation from the mean. So now we can do, I'm just going to put in SS1 and SS2 for the sum of squares. So the sum of squares function, you type in equals and then start typing in sum. But we don't want just the sum. We want the sum of squares, which is SUMSQ. And I'm going to double click on that, SUMSQ, and highlight my deviation scores. Okay, so remember, you need the deviation scores for this sum of squares function to work. We hit enter, and we get a sum of squares for group 1 of 10. We're going to do the same thing. Well, we need the deviation scores over here. Okay, equals the first person's score minus the mean, but we're going to again have to put in these dollar signs. Okay, now I'm going to drag the bottom right-hand corner down. It'll apply the equation to the rest of those raw scores. So now we're looking at the sum of squares for group 2. I'm going to hit equals SUMSQ, and here we go. All right, so now we've got the sum of squares for group 1, the sum of squares for group 2, and now we just need to divide those things by the degrees of freedom. Okay, remember degrees of freedom for each individual group on its own is n minus 1, n minus 1. Okay, well, the first group, the cat group, has 1, 2, 3, 4, 5, 6 people, so the degrees of freedom there is going to be 5. Dog people, there's 1, 2, 3, 4, 5, 6, 7 people, so degrees of freedom is going to be 6, right? Okay, so let's put a little piece here. This is going to be pooled variance, okay? Pooled variance. And I'm going to expand this a little bit. So the pooled variance, okay, is equal to, and I'm going to put some parentheses to help us with order of operations, our first sum of squares plus the second sum of squares. I'm going to close those parentheses off and then divide it by the degrees of freedom of group 1 plus the degrees of freedom of group 2. So again, let's use some parentheses to help us out. Otherwise, you might get the wrong answer. So degrees of freedom for group 1, we said 6 minus 1 is 5, plus degrees of freedom for group 2. Degrees of freedom is going to be 7 people minus 1 is going to be 6, right? So let's see what we get here. Okay, so we've got a pooled variance of 3.35. Nice. This is the pooled variance between the two different groups. And now we can use the pooled variance to help us get the estimated standard error. So what we need to do is we're going to have to figure out kind of this inside stuff and then square root it. So let's figure out what that is. And you can call this part kind of whatever you want. Um, but what it's going to be equal to is, I'm going to throw in some more parentheses. We got the pooled variance. Now it's divided by n of group 1, the sample size of group 1, which we know is 1, 2, 3, 4, 5, 6 people. Okay, close those parentheses off. I'm going to add to that, again, the pooled variance, but this time divided by, oh, and let's throw in some more parentheses. That's going to help us out. Okay. But I'm going to add, or rather, I'm going to divide that by total number of people in group 2, which is 7. 7. Okay. All right, so let's see. Making sure we got what we got here. We got pooled variance divided by N1, 6 people, plus pooled variance divided by N2, 7 people. Looking good. Okay, so that's kind of just this internal piece right here, but we're not done. To find estimated standard error, we need to take the square root of that. So I'm going to put estimated standard error here, and that is equal to the square root of that number. So square root, there's a function SQRT, and then we put that number in there, and that is our estimated standard error, 1.02, basically. All right, So nice. We're getting there, right? We had the pooled variance. We used the pooled variance to help us get the estimated standard error. And now we are ready to get our observed t-score. Okay. So the observed t is equal to mean of group one minus mean of group two divided by estimated standard error. Now, originally, this is kind of an important point to think about. Originally, the one-tailed hypothesis that we made was that dog people, on average, would have, excuse me, a higher extroversion rating than the average for cat people. So X1 and X2 here, it kind of it kind of makes more sense to use X1 as dogs, or dog people rather, the extroversion rating of dog people, because when you subtract out a smaller number from it, you're going to get a positive number, and that's going to give you a positive t-score. And we're interested in something being more than something else. And so the positives make more sense. You could do it either way. You'll just get a negative t-score, and that's not bad. But then when you look up the t-score on the t-table for the critical value of t, well, then you'd want to use the negative value. Okay. And so hopefully that makes sense. You're either asking the question, do cat people score lower on extroversion than dog people? In which case you're interested in a negative t value. Or you're asking the question, do dog people score higher than cat people? In which case you're looking at and wanting to find a positive t value and compare it to the positive t crit. So hopefully that makes sense. So what I'm going to do right now is for this t-score, I'm actually going to, and it's totally cool, you can do it either way. I'm going to put in equals, and in parentheses, we're going to take the mean of the dog people, and this is the mean extroversion, remember, this represents extroversion. Mean extroversion for dog people. I'm going to subtract the mean extroversion for cat people, and I'm going to divide that all by the estimated standard error, right? Mean one minus mean two over standard error. And I'm going to get 1.82. 1.82. Now, again, this would just be negative 1.82 if we subtracted the dog extroversion average from the cat extroversion average, and that's fine. But then you'd have to make sure your interpretation is correct and you're looking at comparing it to the correct critical t value. All right, so what we're going to do now is we've got our observed t, but we also want to know what the t critical is, right? Because we're going to compare our observed t to the t crit and see if it's more extreme and lies in the critical region or not. So what we're going to do is, let's see, I think I need to stop sharing and then reshare the T table with you. Okay, so what I'd like you to do is to figure out what is the critical value of T for a one-tailed test with a significance level of 0.05, where the total degrees of freedom for an independent samples t-test is n minus 2. And that's all participants minus 2. So go ahead and figure that out for me. Okay, so degrees of freedom is n minus 2. There were 6 people in the cat group, 7 people in the dog group, which makes 13. 13 minus 2 is 11. So we're looking for degrees of freedom of 11. We are also making a one-tailed test with the significance of 0.5. So I follow that down to 11, and it looks like our critical value of t is 1.796. 1.796. Okay, so let's write that in. 1.796, and I'm probably going to have to stop sharing and reshare again. Sorry for the technological stuff. Okay, so 1.7, I think it was 796, right? So here's the question of the day. Is our observed T more extreme than the T crit? Yes, it is, just barely. We made it into the critical region, and therefore we can say that there is a significant difference. It means we reject the null hypothesis. What was the null hypothesis? The null hypothesis is that there's no difference between the average extroversion between the two groups. There's no difference between these two group means. But in fact, we reject that null hypothesis and conclude that our alternative in this case, which was um, dog people on average have higher extroversion ratings than cat people, we conclude that that is true, and therefore these two means are significantly different from each other. Very, very nice. However, this is another thing to think about. So that was the t-crit for a one-tailed test. Let's think about what the t-crit for a two-tailed test would be if we didn't know or didn't have any idea about like, well, I think one group will have a higher or a lower extroversion rating on average than the other group. If we just said, I think dog people will have a different amount of extroversion on average compared to cat people, well, now we're going to have to look up what the t-crit for a two-tailed test is with the same degrees of freedom and same alpha level. And I'll just tell you that it's 2.201. 2.201. So if we were making a two-tailed hypothesis and a two-tailed test, would we have found significance? Would we have rejected the null hypothesis? No, we would not, because our observed t of 1.82 is not more extreme than the critical value of t, 2.201. So we would have actually gotten a non-significant difference, meaning we failed to reject the null hypothesis. What's the null hypothesis? The null is that these two means are not different from each other. And guess what? If that was the case, we could not say that those two numbers are statistically significantly different from each other. So just food for thought, right? It really matters whether you're looking at one-tailed tests or two-tailed tests in specific situations like this. Okay, hope that was interesting. Thanks so much, and I'll see you in the next video.